Okay, so I previously asked you to think about how we know the gravitational constant. Um, how do we know big G? Okay. And what you would probably start with is, well, I can just take the gravitational force the Earth exerts on some object. Okay, so here's the Earth. Here's some object on its surface. And if I measure that force, well, then I can just take Newton's law of universal gravitation. F equals G, mass of the object, mass of the Earth, over radius of the Earth squared. Okay, so if I measure the force on the object and I know everything else in this equation, then I know G. But how do we know the other things in the equation? Well, the radius of the Earth is easy enough to figure out. People have known that for over 2,000 years. And the mass of the object is also easy. But the mass of the Earth is kind of a wild card here. We don't know that. And we also don't know G. Okay, so we have two unknowns here. Okay, so if we knew the mass of the Earth, then we could figure out G, because we would know everything in the equation then. But we don't. So we could maybe guess the mass of the Earth based on its density, what we think it's made of. But I think you would agree that that's probably not very precise. Like we would only be able to get the mass of the Earth maybe within like 30% or something like that, because who knows what's going on deep inside the Earth. So you might say, all right, well, let's consider some astronomical observations. Maybe I can go and take the sun and the Earth, and here I can use the force that the sun exerts on the Earth is equal to G, mass of the sun, mass of the Earth, over radius, the distance from the sun to the Earth squared. Well, we know that distance, and the mass of the Earth we don't know, and here we don't know the mass of the sun either. Okay, but we can figure out the force. And in fact, if we do a little bit of work on this, we can do F equals ma, and since the Earth is the thing that's accelerating, me times the acceleration of the Earth. So in fact, the mass of the Earth cancels. Okay, so we could do G times mass of the sun over the distance between the sun and the Earth squared equals acceleration of the Earth. And the acceleration of the Earth we can figure out from kinematics. We can just see how long it takes the Earth to go around and then use centripetal acceleration to figure that out. But again, we still don't know the gravitational... Oops, that's not what I wanted. We don't know the gravitational constant, and we don't know the mass of the sun. Okay, and if you consider more and more situations, what you're going to find is that that's always the case. You're never going to be able to come up with an observation we can make where we can figure out G, because we always will not know something else just looking at, say, astronomy. So what you have to do is you have to do an experiment where you know both masses ahead of time. Okay, so this is the experiment that Henry Cavendish did in 1798. Okay, so Cavendish, in his laboratory, set up a situation where he had the ceiling of the lab, and then from it he hung a wire. And then from that wire was hanging what is essentially a dumbbell. So he had these two masses that were balanced hanging from a wire that was hanging from his ceiling. Okay, so this is drawn in perspective. There's a 90-degree angle there. Okay, and then he set on the floor of his lab some large lead objects like this, so that there was a gravitational force between the objects that were hanging from the ceiling and the ones that were sitting on the floor. So I'll call this big M, and I'll call these little m. Okay, so due to the arrangement here, the gravitational force is going to want to cause this to twist. There's some torque that's exerted on the hanging masses. Okay, and so by using some clever tricks, you can figure out what that torque is. You essentially let the hanging masses rotate over a long period of time, and you can figure out then what force must have been exerted on them. And there are actually some tricks so that you don't have to worry about the distance changing and stuff. You can do this in a way that is a little easier in a few like practical details, but this is the general idea behind this. And so you can basically take as large of a mass as you can get for big M, like several hundred kilograms for those lead masses. You hang as much mass as you can from the ceiling in those dumbbells, and eventually you get a calculation for the constant G, because then you know everything. You have F equals G M times big M over r squared. And because you can measure all those masses independently, and you can measure the force, then you're left with just G. And then, once you know G, then you can go back to these other cases we were talking about up here, and you can actually figure out the mass of the sun. So by using astronomical observations, once you know G, now you know the mass of the sun. And in that first case we looked at, you can plug in G, and now you know the mass of the Earth. So that's in fact how we know the mass of the Earth. We don't get the force from plugging in the mass of the Earth. We get the mass of the Earth from measuring the force. So astonishingly, 200 and some years ago when Cavendish did this experiment, the value he got for G was very close to the modern value. It was within a few percent of the one that we use today. And so this basic strategy for doing gravity experiments is actually also still in use. So this device is called a torsion pendulum. Because you can imagine if you let the thing go and you didn't have all those masses around, it would basically swing back and forth like a pendulum. And because it's twisting, we call it a torsion pendulum. And so torsion pendula are used today to do gravity experiments. When I was in grad school, one of the labs that was in the same building as me was doing gravity experiments, and they were measuring the gravitational force between objects that were, say, 100 grams and maybe a millimeter apart, using a device that's very similar to this. And in order to do those extremely sensitive measurements, you have to worry about airflow. You have to worry about people walking by because it's sensitive enough that you can detect the gravitational effect of a person. You have to worry about cars driving by. So a lot of these experiments have to be done in the middle of the night. And you might have to worry about, whether it's raining outside. One of the things that they noticed is they could detect the difference between summer versus winter in their measurements because the lab is built near a hill, and during the winter the hill was wet, and so it was much more massive than it was the rest of the time. So astonishingly, you can pick up those kind of details from gravitational experiments. So it's really quite impressive.